Hello. This lesson is going to be about another method for solving quadratic equations called completing the square. So when you master completing the square, you'll be able to solve equations like this using this method. There's a couple of things that we have to do first. So we're just going to set this off to the side. And let's talk about some concepts that you have to understand before we can start to complete the square and solve. So in order to complete the square, one of the things that you have to know and understand is the concept of a perfect square trinomial or a binomial squared. So what does this mean? It means you're multiplying two binomials that are the same as each other. So as an example, I have three examples here. I have x plus 3 squared, x plus 4 squared, and x plus 5 squared. And each of these represents a multiplication of a binomial that is of two binomials that are identical. So x plus 3 squared represents x plus 3 times x plus 3. X plus 4 squared represents the same, but with 4s. And x plus 5 squared represents x plus 5 times x plus 5. Now, we can use our knowledge of how to multiply binomials in order to multiply these out. And if we multiplied x plus 3 times x plus 3 using our knowledge of multiplying binomials, we'll get x squared plus 6x plus 9. And then with x plus 4 times x plus 4, again, if you multiply that out, you're going to get x squared plus 8x plus 16. And then with x plus 5 times x plus 5, you're going to get x squared plus 10x plus 25. And you can repeat this, with any number being in the binomial there. However, the reason I did three examples is because there are certain patterns that we're looking at that are going to help us when we complete the square. So the first pattern is that the number in the binomial is added to itself. You can think of it as it being doubled. So 3 plus 3, and that's the 6. And that pattern repeats for each one of these square binomials. Right? So 4 plus 4 is 8, 5 plus 5 is 10. So using this pattern, we can see that anytime you have a binomial square like these, anytime you have one of these, the middle term in the answer will be double whatever's in the binomial. So 6 will be 3, or 4 will connect to 8, 5 connects to 10. And you can say, anything really. So you can say x plus 100 squared, and that will, that the middle term is going to be 200 because it's double. So that pattern is always true regardless of what number is there. Okay. Important side note is that this is the case where if x doesn't have a coefficient. So as long as there's not another number other than 1 here, then this will work. The other pattern is that this number is always that times itself. So 3 times 3 is 9, 4 times 4 is 16, 5 times 5 is 25. And going over here with our 100, right? 100 times 100 is 10,000. So again, that pattern is always there. And if you ever forget this pattern, you can always remake it. You can rediscover the pattern just by multiplying, using your knowledge of multiplying binomials. You can rediscover the pattern. Just multiply some binomials together and you'll see it again. So we can use this pattern to complete expressions that would not otherwise be completed. So for example, what I mean is, if I told you x squared plus 10x, or excuse me, x squared plus 12x plus something, right? What would it take to complete that something? What number would go here in order for it to follow these patterns? So we would look at this 12 and we would think to ourselves, you know what, that 12 is 6 plus 6. And so off to the side, we know that it's connected somehow to x plus 6 squared. Then we can come in here, and since we know it's x plus 6 squared, and we know 6 times 6 is 36, that means we are able to tell that that's 36 there. So if we have a trinomial, if we take half of this linear term, if we take half of this, that's going to give us this number here. And then we can use that knowledge to then find this constant term at the end over here. So that's the pattern for completing the square. Okay, so the reason why we want to know that pattern and how we're going to use it is if we see that we have a trinomial that follows the pattern that was discussed before, that this pattern up here. For example, this one, x squared plus 12x plus 36. Since we know that it follows that pattern, what we can do is we can replace this section right here with what it's equal to. So since this here, this highlighted part is equal to x plus 6 squared, we can replace it with x plus 6 squared, like this. And let me just adjust this, because that should be a plus. Okay, and this move is allowed because this equals this, as we discussed before. So because those two are equal to each other, we can get rid of this and replace it with this. And this is going to allow us to solve the equation, which I'll explain here in a few moments. Okay, so coming over here, right, look at that center number. We see 18. We know that that connects to 9 because 9 plus 9 is 18. So we know that this does follow the pattern because 9 times 9 is 81. So we can replace these three things with x plus 9 squared. Now, what happens if it doesn't follow the pattern? What if it's got something like this? Right? So in this case, we have a trinomial that doesn't follow the pattern. And we see we've got a 14 in the center there. So we immediately relate that to x plus 7 because of that 14. So we're thinking off to the side here, x plus 7 squared. And we say, well, that doesn't make sense because this 12 would need to be then a 49, which it's not. But we can use a little bit of algebra and we can actually turn this into a 49. So all we need to do to turn it into a 49 is to add 37, right? Which because it's an equation, we must add 37 to both sides. And that's going to give us x squared plus 14x plus 49 equals 45. Okay, and now we have our pattern, which we can then replace. X plus 7 squared equals 45. And this is the essence of completing the square. This is what completing the square is all about. We're going to have a trinomial expression that does not match the pattern which we discussed above, this square pattern. So we have to complete the square, hence the name, by changing the constant term so that it matches the pattern, which will then allow us to replace it, which will then allow us to solve. This is very desirable. We want this. It's going to let us solve the equation. So let's do another quick example before I introduce a little bit more complexity. So we might have something like this. Okay, and we can see here, we look at the 16, that immediately makes us think of x plus 8 squared. And because we know that's an 8, we're expecting a 64, but it's not a 64, so we have to make it a 64 by adding 24. And we have to add it to both sides. And that is going to give us our pattern, x squared plus 16x plus 64 equals 25. And now that our pattern is complete, now that we have completed the square, we can replace it with x plus 8 squared equals 25. And again, this is what we want. So there are a few layers, a few levels of complexity here. The first one is that you don't always have to add. Sometimes you can subtract. So for example, let's say you had x squared plus 2x plus 3 equals 7. Okay, we see this 2. We see that 2, which immediately makes us think of x plus 1 squared, because 1 plus 1 is 2. And that means this should be a 1, because 1 times 1 is 1. So in order for this to be a 1, we actually have to take away 2. And that's perfectly allowed. You can, before we were adding, and now we're subtracting, but that's fine. And that's just going to give us x squared plus 2x plus 1 equals 5, which allows us then to replace that with x plus 1 squared equals 5. Oops, it's 5. So that's one level of complexity. Another one is sometimes the middle term is negative. So you might have something like x squared minus 16x plus 80 equals 3. And in this case, when you're looking at the number, you're not just looking at the 16, it's a negative 16. So you think, well, negative 16 would be negative 8 plus negative 8. So we're actually looking at x minus 8 squared, right? That negative sign in there. And negative 8 times negative 8 is positive 64. So we're expecting a positive 64 here. And we don't see that. So let's turn it into a positive 64 by subtracting 14. And that's going to give us x squared minus 16x plus 64 equals negative 11. And that is now a pattern, which we can then replace with x minus 8 squared equals negative 11. Okay, so these are some levels of complexity. However, it does get even more complex than this. So here I have another example, x squared plus 4x equals 5. And in this case, it's actually missing the third piece entirely. You can almost think, or you can think of this as plus 0. There's nothing here. We're missing that third piece entirely. So even though that piece is missing, we can still look at this 4 and know that 4 is 2 plus 2. And that immediately makes us think of x plus 2 squared, which means we're expecting 2 times 2 over here. So we are expecting plus 4 there, which means we're going to have to add 4 to both sides. So we can add 4 here, we can add 4 here, and that is now a complete pattern that matches x plus 2 squared. So we can replace it, x plus 2 squared equals 9. Another thing that can add some complexity is if the center number is odd or if it's a fraction. So you may have equations like this. Right, where you have an odd number in the center. Now, you might wonder what times what equal, or what plus what equals 3. So 3 is double of what, and the answer is in decimal form we say 1.5. However, we do want to get used to those fractions, and so we would say 3 over 2, the fraction 3/2. So looking at this 3, we know that we're looking at the binomial of x plus 3/2 because of that 3. And since that 3/2 is there, we know that this number should be 3/2 plus 3/2, or excuse me, 3/2 times 3/2. So in here, we're really looking for this times itself, 3/2 times 3/2, which is 9/4. Instead, all we have is a 2, which is actually 8/4, right? This 2 represents 8/4. So what we can do is we can add 1/4 to both sides, because this 2, remember, this 2 is 8/4. If we add 1/4 to both sides, this will turn into 9/4, and then this will turn into 1/4. And this is actually a completed pattern, because we have 3/2 plus 3/2 is 3, and then 3/2 times 3/2 is 9/4. So it's still following the same pattern that we talked about before, even though it's got that fraction in there. So we can come in here and we can replace with x plus 3/2 squared equal to 1/4. And that's what happens when you are dealing with fractions or odd numbers in the center. You just have to get comfortable with some fractions in there. Now, occasionally, to add the most level of complexity, I think this is as complex as it gets. Additionally, sometimes the x squared term will have a coefficient. Like in this case, we have a 2. In our original problem, we have a 2 in front of the x squared. Now, this is an issue because none of our patterns that we've discussed before have that. None of them have a number in front of the x squared, a coefficient. So what I recommend, and you'll get different teachers recommend different courses of action. What I recommend is that if you're dealing with an equation, is that you divide everything by that coefficient. So in this case, because we have a 2, we'll divide everything by 2. However, if this had been a 3, we would have divided everything by 3. Or if it was some other number, we would have divided everything by that number. So let's go through and divide everything by 2. So 2 divided by 2 is 1, and we don't have to write that. 6 divided by 2 is 3. 11 divided by 2 is 11 over 2. And then 2 divided by 2 is equal to 1. So now we can more accurately complete the square. We can think about what we need in order to complete that pattern. So once again, we have this 3. Okay, and that makes us think about, let's choose a different color here. That makes us think about x plus 3/2 squared, right? Because 3/2 plus 3/2 is going to equal 3, which means this should be 3/2 times 3/2, which is 9/4. So we need this to equal 9/4. Right now, it equals 11/2. If we turn that into fourths, that will be 22/4. 11/2 and 22/4 is the same thing. Okay, but like I said, we want this to be 9/4. So we need to get down, instead of 22/4, we need to get down to 9. So we're going to subtract 13/4 from both sides. And that's going to give us, if we subtract 13/4 from here, 22 minus 13 is going to give us 9, which is what we want. And then 1 minus 13/4, that would be, remember 1 is 4 over 4. So 4 minus 13 is going to be -9. So now we have our pattern. This is the pattern that we saw before, because it's that pattern, because 3/2 double is 3, and 3/2 times itself is 9/4, that's the pattern that we talked about up here. So this actually completes the pattern, which allows us to then write x plus 3/2 squared equals -9/4. So I recommend that you find a resource. We do have some resources that we're going to be sharing with you, but find a resource that lets you practice this concept of completing the square. And that's going to, once you get comfortable with it, the next step is comparatively simpler. It's just solving, which I'll be going over here in just a moment. Okay, so to solve an equation by completing the square, you first of all need to have gotten your equation into this form. So we've done several examples where we've gotten our equations to this form. Once you get your equation to this form, it's just a matter of solving for x, getting this x isolated, which means we need to cancel these other numerals, these other numbers in here, just so that we can get the x by itself on one side of that equal sign, right? Our goal is we wanted to say x equals something. So in order to begin canceling, we're going to need to cancel this square here. In order to cancel that, we're going to take the square root of both sides. Okay, so the square root cancels with the exponent of 2. Okay, so these will cancel. And that's going to give us x plus 3/2 equals the square root of negative 9/4. Now, this is where knowledge of something called the fundamental theorem of algebra comes into play. So the fundamental theorem of algebra. What the fundamental theorem of algebra says is that the highest exponent that belongs to an x, or to your independent variable, the value of that exponent tells you how many solutions that equation has. So because we're dealing with an exponent of 2, this equation has 2 solutions. That's the fundamental theorem of algebra. So if the highest exponent was 3, it would have 3 solutions. If it was 4, it would have 4 solutions. And the reason that that matters is because when we cancel this 2, we're actually getting rid of one of the solutions. And that's not great, because quadratic equations have 2 solutions. When you solve them, you have to get 2 answers, 2 solutions. So how do we get around this? Well, whenever you cancel a square, an exponent of 2 like this as part of completing the square, you're going to then put a plus or minus sign in front of the square root on the other side. What this does is it preserves both answers. So yeah, we are missing now the 2, but now we have an answer that's going to be positive and an answer that's going to be negative. Or not that the answer will be positive or negative, but there will be an answer where you're adding square root of negative 9/4 and an answer where you're subtracting square root of negative 9/4. If that doesn't make a lot of sense to you, think of it like this. If you had a really simple equation, something like x squared equals 9, right? How many solutions are there to this equation? And now you might say, well, x can equal 3. Yeah, that's true. However, x can also be -3, because -3 times -3 is also 9. So in this case, you have 2 solutions, one where x equals 3 and one where x equals -3. So the way we represent that is when we cancel this square root of 2 by taking, or this, when we cancel this exponent of 2 by taking the square root, we're going to put a plus minus in front of that square root of 9. So that's going to give us x equals plus minus square root of 9. And then the square root of 9 is 3. So x can equal +3 or x can equal -3, which is what we got before. So that's why we do that plus minus sign. basically, anytime you cancel a exponent of 2, you need to put a plus minus sign in front of the square root on the other side. And that's going to preserve both answers. Otherwise, you're only going to get stuck with one answer, and it'll be that will be incorrect because it's only one instead of 2 answers. Anyway, so now we have this plus minus sign. Let's go back over here. We canceled the square root of 2, or excuse me, we canceled the exponent of 2 by taking the square root of both sides. And now we need to cancel this 3 halves. It's plus 3 halves. So the way we cancel it is we just subtract 3 halves. And so that's going to give us negative 3 halves on the other side, plus or minus square root of negative 9/4. The negative 3 halves wouldn't subtract from the square root of negative 9/4 because these are different types of numbers. So this number is not under a radical. This number is under a radical. They don't play nice. You can't, they're not like terms. You can't combine them. So in this case, this is very nearly complete. So you cancel the exponent of 2, subtract over or possibly add over if this is negative, the number here, and then you just simplify. So in order to simplify the radical, you're going to use your knowledge of simplifying radicals. Since it's negative, there's going to be an I in the front. And then the square root of 9/4 is going to be the square root of 9 over the square root of 4, which is the square root of 9 is 3, and the square root of 4 is 2. So this 9 would be a 3, this 4 would be a 2, and that would be your solutions. And then finally, what's very common is to actually separate the 2. So we can write x equals negative 3 halves plus 3 over 2i. Usually we put the I after the number. So instead of writing it like this, I 3 over 2, we put the I after, almost like a variable. And then one where it's plus, and then one where it's minus. So those are our 2 solutions there. And that is the complete knowledge of how to complete the square. So before we finish our lesson, I'd like to run through a problem from start to finish. And this is the problem that we had at the start of the lesson. This is the one that I put up there, and now I've moved it here. So let's solve this problem from start to finish using the completing the square method. So our first goal is to set up our pattern of a square. In order to do that, let's get rid of this 2 by dividing everything by 2. So 2 divided by 2 is going to be 1, which we can get rid of. 3 divided by 2 is just 3 halves. Negative 5 divided by 2 is negative 5 halves. And then 2 divided by 2 is 1. Okay. Now, we know that this term should be double of whatever's going to be in our parentheses. So we're thinking of our parentheses. And we know this is double, which means our parentheses is going to have 3/4 in it. Right? So 3/4 is half of 3 halves, or you can think of 3 halves is 3/4 plus 3/4. That means that this number should be 3/4 times 3/4, which is 3 times 3, which is 9 over 4 times 4, which is 16. So we're expecting 9 over 16. That's what should be here. Instead, we have 5 over 2. So let's turn this into 16ths in order to figure out what this needs to be. So this is going to be in 16ths, this will be 40/16. And we would need this to be, and it's actually negative as well. We need this to be 9/16. So we're going to need to add 49/16 here to this side, and we're going to need to add 49/16 to the other side. So when we add 49/16, that's going to give us plus 9/16. And we're going to add 49/16 over here. So 49/16 plus 16/16 is going to be 65/16. 49 plus 16 is 65. So now we have our pattern. 3/4 plus 3/4 is 3/2. 3/4 times 3/4 is 9/16. That's our pattern. So we know that this is going to be replacing this. So let's do that now. X plus 3/4 squared equals 65/16. Okay, now that it's set up in this form, we want to solve by canceling out by isolating the x. So let's cancel out this 2, and then we'll cancel out this 3/4. So to cancel the 2, we're going to take the square root of both sides. This square root is going to cancel that exponent of 2. And that's going to give us x plus 3/4 equals the square root of 65/16. And because we canceled out that 2, we're going to have a plus minus sign there. Now, we just need to cancel this 3/4. So let's subtract it on both sides. And that's going to give us x equals negative 3/4 plus or minus the square root of 65/16. So x is now isolated, and now it's just a matter of simplifying as much as we can. So let's simplify here. 65 can't be simplified in a square root, but 16 can. So when we have the square root of 65/16, that's really saying the square root of 65 over the square root of 16. And the square root of 16 is 4. So we can write this. This is pretty well simplified. Some people might adjoin the denominators and just have -3 plus or minus the square root of 65/4. But I think this is okay. And then we can separate one where it's plus and then one where it's minus. So we can put x equals -3/4 plus, and I'll just copy this. And then one where it's minus. X equals -3/4 minus. And these are the solutions to the equation that we started with. So we went through a problem from start to finish. We started off by setting up our pattern, making sure that we didn't have a number, a coefficient in front of the quadratic term in front of the x squared, making sure that our constant term matched with our linear term using our parentheses as a guidance and following the pattern which we established earlier. So we set up our pattern and then we replaced it with the parentheses because these are equivalent. And then we solved by isolating the x until we got to here. X was now isolated. And then it was just a matter of simplifying the radical. And sometimes when you simplify the radical, it simplifies down enough that you actually can add and subtract because the radical will disappear. In this case, However, we still have a radical, which means it's going to stay. And that's completing the square. That was a problem from start to finish, completing the square.